Testing, 1, 2. We're going to get started in a second. Testing, 1, 2. We're going to get started in a second. Alright, here we go. Hopefully you can hear me. Got a couple people watching. Um, Figured just kind of for record purposes and educational purposes, I figured I'd just live stream and record me going over some data that I collected today during a kind of interesting troubleshooting that I had today on it was a Generac 2.4 liter Mitsubishi. I think it was a 27 kW protector series with an evolution controller. I'll bring up right now. This is my scope. This is the eScope Elite. It's an 8-channel scope. So kind of a backstory on it. I guess few, few, a couple companies had been there before we had got sent out. Another tech went out, and he kind of nailed what was happening right off the bat. He didn't have a scope on him, so I'm always advocating for use of a scope during diagnostics. Anyone who knows me uh, knows that I go a little crazy over oscilloscopes. So basically, he went and looked at the timing. It was backfiring, so it would crank. All of a sudden, it would backfire out the exhaust consistently. It wasn't like it was a alternating backfire where sometimes um, it would backfire. You'd go, out the intake and then backfire out the exhaust, almost like a lean miss or something. This was more of a straight up, just a straight backfire out the exhaust. So kind of looking like it was timing. So he pulled the timing cover off. It's pretty easy to do on these units. And he verified timing, and it turned out to be good. So, he's an experienced technician, and it still sounded like timing to him the way it was acting. So we had talked, and I mentioned possibly using my scope coming in, and I'd be able to verify timing and stuff a little easier. So I got sent there today. One of the coldest days so far this year. It wasn't fun. Just trying to get all the gear outside, and it was windy and cold. So, but I went there first. I checked fuel pressure. Fuel pressure was good. So wanted to make sure there were sparks. So I did do so I just hooked up one channel of the scope to like ignition coil 1. So this engine, let me see if I can pull it up here, just for a little overview. It's the 2.4 liter. And actually, hold on one second. I'm going to blank my screen here for a second. I don't want to. Actually, I can pull it up here. We'll see it. Boom. Just don't want you to see my Generac account there. So, anyways, it's a 2.4 liter. This doesn't matter right here. This is the R200 controller. This was on an Evolution, but they used the same 2.4 liter Mitsubishi. Actually, a really good unit. It's probably my favorite liquid cooled, smaller, residential, light commercial generator out there. Really, not many problems with it. It doesn't have a coil pack. They're individual coils, and they're mounted like 4 on a bracket up front. So let's see if I can bring it up here. So there's four individual coils on a bracket, and actually I got a couple good pictures here. So looking at figure 8 here, you can see that bracket, someone's actually disconnected it here and laid it back on the engine, and that's actually to do there's a couple things for the timing belt, and also it uses a mag pickup for the cam sensor. So you got a mag pickup cam sensor in the front here. I think it's a variable reluctor, so the faster it spins, the more voltage it'll create. There's only one trigger, and it's an actual magnetic trigger, and it goes right here. Now, pay attention to this. This will come into what I think is the problem later on. There's actually 4 holes that you can actually thread it into here, but they're indicating the one with the dot is where you actually want to thread that into. Here on figure 10, you can see it a little closer. So that mag pickup will thread right through, and you're supposed to gap, this cam pin that's right here. You're supposed to gap that. And what are they saying for a gap? And that really doesn't matter as far as my troubleshooting goes. 1 inch, let's say using a brass feeler gauge, set the cam sensor gap to about 15 thousandths. So that's that. So they show you the coil packs, and it kind of on figure 8 here you can see. So there's individual harnesses. You can see they're labeled. So that's 3 right there. So coil pack 1, 2, 3, and 4 is labeled. So let's do this. I also want to take, just for notes so I can review back to it, pull up a notepad here. Okay. So let's find the firing order on that, which from what I see, for the firing order on that engine, it's 2.4 liter, 1342. Firing order 1, nope, 1, 3, nope, 3, 4, 2. Okay. Firing order is 1342. We'll save that. We'll leave that right there. So, back to my service documents. 1342. So now I'm going to bring up kind of the first waveform that I've captured. We're going to save this. Let me see one thing. All right, let's do this one first. Load data. Okay. So basically, with no sync, I hooked up. I have an 8-channel scope. This is a plot of the actual cylinders firing here, the ignition coils. I back probed all 4 ignition coils. And what's really nice about this scope, let me zoom in here. You can zoom in, first of all, yeah, you can zoom in and look at the data. So you can see a repetitive pattern wherever you go. You know, whatever one you want to start on. Let's start on the red, green, yellow, blue, red, green, yellow, blue. So you can see we have a consistent firing. Every cylinder's firing. We're not getting any dropping out. So right there, hooking just 4 back probe connections, we can see we have we have a good ignition signal. We're firing on all coils, right? So where's this backfire coming from? It could be a regulator. We're kind of proving right here ignition's not dropping out, so it's not the case of a cylinder going dead and then you know, filling up, and then all of a sudden we're firing and, you know, backfiring out the exhaust. So we got a pretty good ignition control here. We can, let's zoom in on one cylinder here. So, and it, actually, that's not good. So it's all how you scale. I'll zoom in on these. So you lose resolution when you scale in a certain way. So I'll take a zoom window and do this. All right, so we can see what our burn time is right here. So let's see. So if I get some cursors, I go there, and I go here. Okay. Right now, that's a long burn. That's a 2.458 millisecond burn right there. Maybe 2.3. But we're not firing. We got no fuel. We're not running any. This is cranking too, so we're gonna have a longer spark duration there. With no fuel, so that's going to throw it off. But we have what looks like a pretty lean burn cylinder right here. And all these, when we're running natural gas and propane, a lot of guys that are watching engine diagnostics with gasoline engines, the waveforms are going to look a little different on a lean burn engine. So anyways, this waveform is useful. We can see we have a consistent ignition pattern. We got ignition control. We definitely have the pattern red, green, yellow, blue, red, green, yellow, blue, 1, 2, whatever the firing order is. But we don't have a sync. We don't know what is cylinder 1 and cylinder 2. So what we have to do is put a sync on that. So what I did, kind of kill two birds with one stone, we want to know, you know, timing isn't just about one thing. You can have mechanical timing, and then you have ignition timing. So you can have good mechanical timing, but your ignition timing can be off, whether it's through an electronic, you know, a module that's causing the timing to be off, or a sensor, or a reluctor wheel that's moving. So timing can kind of go wrong in a couple different places. You can have injectors, you know, say a control module on, if it's a diesel when the injectors are off, or you actually slip timing between your cam and crank correlation. So to kind of get you best bang for your buck with a test, the next test I think I should have done, which I did, not next test I should show you, is this one. So let me load it up. And I'm doing this on my home PC. I'm trying to load them off of my my tablet that I use today. One other thing. Here's a good thing. So this is me connected to. So I need to know if the cam sensor is working and the crank sensor. By the waveform I just showed you, you can deduce that they are working, because unless you get a good cam and crank signal, the ignition control module will not turn on spark. So I'm kind of going backwards here, but this is a plot. The yellow is a plot of the magnetic pickup. It's counting the flywheel teeth. And what I can do here, we'll zoom in and just see the individual teeth. And you can see the signal as we crank, the voltage gets bigger or increases. That's just the nature of the style sensor we have. It's not a Hall effect sensor. It's not, you know, it's not using 5-volt reference. This actually creates the voltage. It's a magnetic pickup. So looking at this, you can see each of these little spikes here actually represents a tooth on the flywheel. Looking at this data, it's really tough to see what the actual frequency of the generator is, what, you know, the rotation speed of the crankshaft. So one of the neat things about this scope we can do is we can process this data. So if I take channel 1 and I process it as a frequency plot right there, it takes that information. So each tooth, so many teeth go by in 1 second, and that's gonna be a frequency, and that plots this as this frequency in hertz. So you can look at, like right now, we're cranking, and we're going to start at 260 hertz because there's some like, it's the meter's not zeroed out. There's a bias on this, on this scope. So, and you get some noise from the battery charger and the other circuit, so you get some ripple. But once you start cranking, this is an accurate signal. So if you took off, and we can actually, let's do this live, you know, just to kind of prove it for myself also. So this is the speed of the engine going up and down, basically going from 400 hertz up to 500, about 600 hertz. So kind of doing this live, maybe it would make me look like a fool, but let's see if we can find how many teeth are on a 2.4 liter Mitsubishi. Let's see if the old Google will work. Let's see. .4 liter. Hmm. 162, maybe. Let's see. FW 162. I don't know. pixels. I don't want to count it. Let's see if that math works. Okay, so 162. So how do we do this? I know the math. I've done this before. I can actually show you on a different waveform. So let's just take 600 cycles per second. So 600. Let's take the calculator. That's in a second, so we want to get revolutions per minute. So our top, we can see, if I get my cursor, we're at, about 600. So where'd that calculator go? All right. So 600 cycles per second. So we want to get 2 minutes, so we times that by 60. All right, that's 3,600. And what do we say? 162 teeth. That's what we're going to go with for now. 162. All right. So let's take that 3,600, divide that by the amount of teeth. It's about 222 RPMs. That's the cranking RPMs. So you can tell your cranking speed based on flywheel frequency. Kind of a neat trick. And we may be able to, in the next, actually we're going to do this 2 different ways. So let's go back to that frequency plot. So let me load this up. Load my passport. Okay, so we know a 4-cylinder, so between, well, let me get this up here. So let me get 1 full cycle in here. Okay, so 4-cylinder, so we know, actually let me zoom out a little bit. Let's go from blue to blue. So we know from blue to blue is going to be 720 degrees because our crankshaft is going to spin twice for every 1 revolution of our camshaft. So let's get the cursors. And I'm going to line it up there. So now we're going to put it here. What I'm going to do, so that's 720 degrees there. So if I hit marked cam, that gives us 720 degrees of rotation. So we're overlaying the cam over the crank, and if you look at here, 203 RPMs, and if we go back, 222. But you got to keep in mind that waveform that we originally had, the frequency was going up and down in like a sawtooth pattern. So we're basically we're right on, depending where we read this. Depending where you hit mark this cam, you're gonna either increase, but we're in the ballpark. That shows that frequency plotting on the crankshaft does actually work. So this is not only really, I'm not only doing this for just educational purposes, and I really want to highlight the uses of a scope in troubleshooting. So I feel this is going to be helpful for people to see just how much information you can get just from connecting a couple wires. And you're actually going to see a little more as we go on here, just how useful a scope is. Anyone who works with me knows I say it every day. I'm kind of the crazy guy who keeps buying oscilloscopes, but working in the generator field, and we don't really have a lot of access to diagnostic scan tools and stuff. We have them. There's factory scan tools, Generac, GenLink, and Kohler, SiteTech, and all that. But really, it's not as refined as, let's say, a snap-on scanner or something. So having a scope really does help. So, so the next plot you can see we're going to pull up is a in-cylinder overlay. So this is showing that we do have a good ignition control. There's no dropout. Let me reload it again. We're going to zoom out to full. So if we zoom in here, we proved by hooking up 4 wires that we have no ignition dropping out. We've tested the fuel pressure. Fuel pressure is good. We got no problem with the ignition. We've tested the magnetic pickup. Let's go here. We've done, actually I can't load it from there. Hold on one sec. Let's go here. Hold on one second. So the mag pickup, because I have this open. Hold on, I can't do that. Let me load here. Load my passport. Load. So this is the mag pickup signal. We know we got good mag pickup. So now we got to look at cam control and cam sync issues, the cam pulse. And that's derived off of the cam gear, and there's a magnetic pin that goes in, as we showed over here. That magnetic pin right here is going to create one pulse. So looking at this waveform right here, zooming in on it, since there's 162 teeth on that flywheel, you're going to get 162 pulses per revolution, and you can see them here. So each tooth is going to create one of these pulses. And again, I showed you the frequency plot and how we derived the RPM of the engine by taking the frequency, timesing by 60, because that's cycles per second, timesing it by 60. So let's just do that again. So we're about 600 cycles per second times 60. Nope, hold on. 600 times 60 equals, divided by 162 teeth on that flywheel, 222 RPMs cranking. So we got good cranking speed. We got good crankshaft signal from the magnetic pickup. So let's load in the next, probably the best waveform on this. And like I said, we know because we have ignition that we do have a crank and a cam signal. If you're missing that, if you're missing the cam signal, you're not going to get an ignition control. Sometimes some engines will fire, like a waste spark engine will fire basically on crankshaft space angle. But I don't think that's the case on this. And that's kind of goes back to not having a lot of the diagnostic data on these engines that you would normally have in the automotive sector. So let's load this up. Go back to, so here we got to get the one with the sync. So this is probably, okay, this was the first one that kind of let me know I was off. So let's zoom into here. So right here in the yellow, let me shut off green here. This yellow trace is a pressure transducer. Let me shut off the red. Let me shut off the blue. This is a pressure transducer. And I'll overlay some cursors so you can see what it is. So basically, I have a pressure transducer that reads the pressure in the cylinder in cylinder number 1. So this is cylinder number 1. Let me get some cursors. I'm going to put them on top dead center. So this is going to be top dead center. You know, top dead center is going to be the highest top dead center of compression. So the highest point of compression would be top dead center. And there's some signatures that you can look for on these waveforms. If you looking at this waveform, let me do this real quick. Let me go to scope. Let me go to, let's see, pressure transducer. This is the company that makes the scope. So if you look at in-cylinder pressure testing, that waveform with the peaks, every one of these spots on that waveform means something. This is a cranking waveform, so you're going to notice that during the exhaust part of that cycle, we're still below 0 psi, so we're in a vacuum, as opposed to, let me go to another section, when you're running or idling, your exhaust, you're going to create an exhaust pressure or a little over 0 psi. Actually, let's use this chart so I can kind of show you what these mean. So if you look at, this is top dead center of compression. So the cylinder is in the pressure transducer is in one cylinder. So you're reading the pressure of that one cylinder. So as the engine cranks, you're going to create pressure. Okay. Now you're going to get top dead center. Now, if you do not lose any pressure through the rings, the second side of this compression tower is going to be the same slope and angle, and it's going to be even. So any towers that are leaning can mean that, like, you have bad rings, you're leaking pressure or whatever. So I don't want to get too into depth onto this, but just know that each of these portions or sections of the in-cylinder pressure waveform, definitely means something. It's not just a crazy squiggly line. So now, as the piston's traveling down towards bottom dead center, it's going to pull a vacuum, okay? Because we kind of started in vacuum by pulling in fuel and air, and then we compressed it. So we're returning down to that state. So you really should return back down to where you started with. If you lost air out at top dead center, you would pull more of a vacuum here because you'd have less air to return to the normal state. Now all of a sudden you see the pressure rise, right? But why would it rise before the piston's still traveling down, so why would pressure rise? Well, what happens is the exhaust valve opens, and the exhaust is open to atmosphere, so the atmospheric pressure spills into the cylinder. And you can see here, this is top dead center, this is bottom dead center, and this is a camshaft timing card, and you can see it shows where the exhaust valve opens. It's opened as the piston's still going down. So you can tell just by an in-cylinder pressure waveform when your exhaust valve is opening. You can tell if your rings are bad, if you're leaking. You can tell if you have good compression. So now we can see right here, each of these marks, this is the scope. When I put cursors on each of these towers and then hit mark cam, it overlays these pink marks. Each of these is 90 degrees. No, 30 degrees. Each of these smaller ones is 30 degrees. So 30, 60, 90, 120, 180. Did I count that wrong? 30, 60, 90, 120. Why am I seeing more? 30, 60, 90, 120, 150. Oh, I skipped the 150. 180. So you really want, I guess a rule of thumb is between 30 and 60 degrees, 30 and 50, 30 and 60, you want your exhaust valve to open, okay? You can get a cam chart over here to look at it. Now that atmospheric pressure spills in through the exhaust valve. Now the piston starts driving up. Now as that piston starts driving up to top dead center, you're going to get turbulence. So these waveforms going up and down here is turbulence. Then all of a sudden over here on the intake we drop. Well, there's overlap, the intake and the exhaust. So this one's a little harder to tell. So the exhaust and the intake valve are open there's overlap. So they're opened at the same time for a second over here. So we're at top dead center, the intake valve opens, then the piston starts traveling down and we start pulling our vacuum again. Once we get to bottom dead center, the piston's going to start driving up, and kind of like over here on your exhaust valve, your intake valve is going to go close between 30 and 60 degrees after bottom dead center, and we're going to continue our compression stroke. So all of these portions of that in-cylinder waveform mean something. Anyways, so let's go back to this waveform. So here's that waveform. It's not as defined because we were overlaying it over an idling waveform. This is a cranking waveform. If I hit mark cam, this section now, we can see we're running at we're cranking at 194 revolutions per minute, close to the 222. And you know, keep in mind I'm cranking this thing all day, so we're dropping battery voltage, and you know, so I'm starting to lose cranking speed. So we can see that I have, you can see right here, this is not going to really be defined, but you can see that about between 30 and 60, so I'd say about 40 degrees, we have our valves opening. You can see we start to go down here, so I can see exhaust and intake valves opening here, so I'm happy with that waveform, especially for an idle, a cranking waveform. So let's go back into here. Now I'm going to load this. Now I'm in cylinder number 1, which is the yellow, and cylinder and ignition coil number 1 is the red. And if we notice here, here's the problem. Really, when we fire, we're about, what, 10 to 20 degrees advanced for timing. Why am I firing way before top dead center? So we're talking, if I grab these cursors, I am about 194, I'd say about 180 degrees advanced out, right? So because taking into account, we're going to be advanced a little on this, you know, you don't fire right at top dead center, you're advanced. So why is my cylinder 1 coil that's labeled cylinder 1 180 degrees off timing? Now this engine supposedly ran from the factory. We've had a few companies work on it. So why am I firing? Why is this coil labeled cylinder number 1 firing 180 degrees out? So after this waveform, I decided to rehook up all 4 ignition coils plus the pressure transducer. So now I got 5 channels running on the scope. So let me load up that one, and I'll show you what the problem was. This is gonna end in a second here. My best Bernie, and I think it is. Is it this one? Nope. Hold on. Load. Boom. I think it's this one. What's going on here? Nope. I had it. Give me 1 second. Load. Where did I put it? All cylinders. There we go. This is the one. All right. So let me take this. We're going to highlight 720 degree rotation. We'll bring in the cursors. So now I got the fuel off when I'm cranking this. Now I'm looking, our red cylinder here, that was the red one we were firing, and it may have changed colors, but we were firing, if you remember, we were firing 180 degrees So it was this cylinder that was firing, labeled 1. This cylinder was definitely, this pressure transducer was definitely in cylinder number 1. Very hard to mistake on a 4-cylinder engine. With plug wire number 1 was going to it. The plug wires are actually labeled. Each coil, their individual coils, the harness in each coil has a label on it. So the harness connector number 1 was plugged in to the coil with spark plug wire number 1. Spark plug wire number 1 was going to cylinder number 1, but we were firing 180 degrees out. What would explain that? Did Generac wire did they put the wrong labels on the coils? Who knows? This thing was apart. A couple different companies were working on it. So basically what I did, being cold, I've shifted, because I have a good ignition pattern that'll fire this thing. So basically what I did is I rearranged the wires. So this green cylinder here, which was like on, I think, number 3, cylinder 3, coil 3, marked, the harness was marked 3. I put that to cylinder number 1 and basically shifted the whole firing order down one sequence. And basically driving home, I was like, well, how could that happen? It makes no sense. I came home trying to look at, trying to find pictures. I want to go to it tomorrow and look at I found the schematic. So I want to look at the wiring number, let's say for cylinder number 1, the actual wire number on the wire itself, not the loom. The loom had a label on it. I want to see if the wiring number matches cylinder 1 for cylinder 1 and all the other cylinders. And as far as timing goes here, let me mark I marked the cam here. Bam. So I marked the cam. And this shows, I think we got like 14 degrees. So if I load that there on that cylinder firing, on that coil firing, on the kick there, we're about 16 degrees advanced, which makes sense after adding that. When we looked at that other one, it was like 194 degrees advanced before top dead center compression, minusing like 14 to 16 degrees of advance. That brings you exactly 180 degrees out. So why would we be 180 degrees out? Could the ignition module go wrong? You know, could there be a problem with that? Nah, it seems to be working. It's a possibility. Were the labels labeled wrong from Generac? I don't know. Possible. And then I'll be able to get the answers to these things, and this is just me kind of going over it in my head. But one thing I was thinking, and it happened, I saw it when I was looking at these pictures. Another way it could happen is looking at this right here. This cam gear has 4 holes on it where that cam pin goes. That cam pin only creates 1 spike, and the ignition module will build the firing order based on that pulse. It creates 1 pulse per revolution of that cam, and then it's going to start with the firing order. So basically it sees that little pulse, and then it goes fire cylinder 1, 3, 4, then 2. Sees the pulse, 1, 3, 4, and 2. So every time it sees that little pulse, it starts on cylinder 1, 3, 4, 2, and it just keeps repeating. It also uses the speed of the crankshaft to know where it is in between each of those. So it basically, it's an equation. It is an algorithm. It builds that firing sequence off a crank angle space and that cam angle space. If someone had put this pin in a different spot, it could make that, I don't know if we'd have to do 90, because since the cam only spins once for every 2 revolutions of the crank, it's kind of hard to think of this. So if we're 180 degrees out on the cam, I don't think you could be Well, no, if you're 180 degrees out on the cam, so every so 1 degree on the crank does not mean 1 degree on the cam. Um, 1 degree on the crank. Let's see. 1 degree on the cam equals 2 degrees on the crank. So 90. So yes, someone could have put this pin one ahead. So you're supposed to put it where this dot is, but if someone put the pin here, that would shift that firing sequence 180 degrees. Even though it's 90 here, like I said, it's a times 2. This will spin once for every 2 of the every 2 revolutions of the crank. So if we're 90 degrees, the crank's going to spin 180. So we're going to be 180 out. I wonder if the pin had been put in a different spot here instead of here. That would shift that firing sequence 180 degrees. 1, 3, 4, 2, starting 180 degrees out. And even if that's not the case, that's kind of a good thing to know, because if on a 4-cylinder engine this has 4 equal quadrants, say that pin, and they do snap, people adjust these wrong. If you put that pin here, you could just rearrange your spark plugs, your coils 180 out, and you could correct for that. So did someone do that? I'm not sure. So I thought it'd be interesting to go over it online. I'll probably be the only. I see 2-3 people were watching it. I'll leave it on my YouTube channel. Maybe someone comes across it. Leave a comment on what you think happened. Hopefully you can see how much information you can get from the scope. I kind of went kind of rambled on, but it's definitely a useful tool. Just on another thing on this scope, what you can do here, I'll show you a couple other things here. This scope can actually, you can provide duty cycle control. So there's terminals on it where I can set the duty cycle, and let's say you wanted to flow test an injector, you could start it and run it at whatever duty cycle you want for however long amount of time, or you can do a 5-volt output. So you can go, you can turn, provide 5-volt reference to sensors and stuff. So kind of a neat additional thing. That's not why I get the scope, but it's kind of something that can help out whether you want to drive duty cycle to an actuator or whatever. And it can control really any voltage, 5 volts, 12 volts, because it's just a pull down circuit. So say you got 12 volts going to an injector, you bring a ground to the one terminal on the scope, and then go out of the other terminal, the pull down control terminal, to the injector, and that'll pulse it at whatever duty cycle you want. Kind of neat. It also has a misfire detector, and basically what it does is it looks at the crankshaft speed, just like I showed you on that waveform. It can tell every time a cylinder fires, the crankshaft frequency will speed up, then slow down. So it can calculate misfires based on your crankshaft teeth. Just to show you that one more time here. If I load this up, let's load this up. I'll go back to this. So that's the crankshaft's speed. That's the crankshaft, each teeth on the crankshaft, right? But if I process the data, it will put a frequency plot on it. And each of these, now this was, I think this was running. Each of these is a cylinder firing, so you can see it fires, slows down, fires, slows down, fires, slows down, fires, slows down. So if you were missing, they're all equal segments. It's a repeating pattern. If in this pattern you saw every, one every four did not speed up, well, you would know that that cylinder is misfiring. And if you put a second channel as a sync, on a known cylinder, you can correlate using the firing order which one is misfiring. So it's a simple way to do a misfire test. Then it also does a cranking compression test. Let's see where I can see that. Tools. Basically, the cranking compression test is just by voltage. When you're cranking an engine over, as the cylinder's coming to top dead center, it's going to be harder to, like if you were barring it by hand, every time it builds pressure, it's going to get harder to crank, and then you're going to get over top dead center, it's going to get easy, and then the next cylinder is going to get hard. So it'll graph the voltage up and down, and a cylinder that has equal compression on all cylinders will have very all the spikes, all the voltages will be, all the voltage towers will be even. So that's one of the neat things it has on this. The last thing, or not the last thing, a couple more things, it has an ignition analyzer. So basically, it'll graph burn time, which that's important to tell, like for to look at if you have a lean cylinder, a rich cylinder. Ignition coil health, and also show you the primary and secondary ignition voltage here, and you can graph them all and see if anything's dropping out. You can graph the kV, and it'll turn up bright red if we're over 20,000 kilovolts. You can analyze the data here. This is some simple data here. So this is just overlaying cylinders over each other, so it's going to stack them all up, so you can see the burn time on this one is shorter than this one. This is just a demo running. You can see I don't have a spike here. You can analyze each cylinder against each other. You got the dual scope here. This is just a strip chart rolling here, and this is a stacked scope here, so it's going to overlay all those. And the next tool, really cool tool, is this, the engine analyzer. Let's see. There we go. I'll put it in demo mode. Let's start off with compression. Okay. Oh shit, I didn't do it. Here we are. Continue. So right here, you pick your engine. You can go generic. So let's just say generic. Let's go to a 4-cylinder. Boom. Okay. We analyze the data. And did we analyze it? File. Let me load this again. Oh, I did something wrong here. Oh. Let it pop up here again. Boom. Just put it on demo mode here. Tools, engine analyzer. Understand. Compression. Boom. All right, so let's just take. Actually, let's take the engine we were working on. Where we're on a Mitsubishi. Say a 2009, 2000. Say we're on a what? 2.4 liter. Okay, we analyze it. Okay, so this automatically, as we went over what the towers look like, this is automatically analyzing the data, and it's seeing if you're advanced, the vacuum. So when you hook this up, you have to hook up I have a vacuum transducer. I have a trigger to a coil, an inductive pickup for a ignition coil. I have an exhaust pulse sensor. I use that on the misfire. Um, and the transducer for the cylinder. So when you measure, it'll analyze this data, and those lines that I had to apply with the cursor, it'll keep them in line here. And you can see this pocket right here we're opening. If each of these is 30 degrees, where, can I pause this? I think I can pause it. I can't pause it. Pause. So you can see that this is, yeah, I can do that. So this is open in about between 30 and 60 degrees, more like 45 degrees before bottom dead center. And then you can see the pressure raises. This is a running waveform, and this is a demo. This is an actual real capture from a real engine that they load on, so you can kind of get used to using the tool and see what a good waveform looks like. And then it'll do a report. You can create a report. This one's not complete yet because it's a demo. So that's the compression side of things. And then the misfire is kind of neat. So when you do the misfire, you got to change it to a different configuration. We got the 4-cylinder here. And now the misfire will have a counter. So when you set it up, you got to set up your sensitivity and your triggers. Then the misfire uses like a Venturi tailpipe sensor with a vacuum pressure transducer that will create a vacuum pulse when the cylinder misfires. It actually, when it shoots the other way, there's basically a tube with a little Venturi in it, and they're measuring the pressure at that Venturi. So when you get a misfire, air is going to rush the opposite way. You're not going to get a normal pulse. So normally you read just the exhaust pulses if you're just looking for like if you're just doing it like a drivability issue. If you want to see if every cylinder's firing, you can tell a lot by just looking at exhaust pulses. This adapter that they sell actually amplifies the misfire. I guess instead of trying to explain it, we got the internet over here. Let me show you what it is. This is a really good, unbelievable, let's see, I don't know if it's, so, yeah, here it is. So basically, it's this right here that clicks on, and air shoots the other way. You put your vacuum transducer here, and basically the change in volume from a regular contributing cylinder to a misfire is going to get amplified by this. And actually, what's really neat on this site, they list their patents. So like you can look at the patents, and I kind of what if I can look at that now? Let's see. Let's see about ATS. Here we go. Let's see if we can Google it. Yep, right here. So I love looking at patents. So basically, it's showing how, and it's the original documents they submitted for the to get the patents, and explaining what, you know, what they actually get into explaining waveforms and what a bad waveform will look like, and you can read basically the whole background of the invention and their whole system. Four-cycle internal combustion engine has 4 cycles, 4 strokes that occur in 720 degrees of crank rotation. Each cycle occurs within approximately 180 degrees of crankshaft rotation. What does that mean? Oh, each cycle occurs. The 4 cycle, yeah, 4 cycles. So you get 4 sections of 180 degrees of that 720, and that makes up your whole 4-stroke combustion cycle. So basically, I mean, they've done their homework on this, and all of this is built on. Here's something a lot of people don't know. This is all National Instruments software, right? Their scope is built on National Instruments, and I like that because one of their older scopes, actually, you can read it right through LabVIEW, and LabVIEW is a really useful tool where you can get data acquisition devices, and that's what a scope is, and actually build your own program on it to collect whatever data you want. So they've basically built this on LabVIEW, and to kind of show you something neat, one of the tools we use in on generators is PSI software, and PSI software is also built on LabVIEW. So kind of looks the same. So if you look at this eControls setup, eControls basically took the LabVIEW program right here, and you can build your own front end, the user interface. And let's see. So like basically, let's do this. No, we ain't gonna do that. Stop. No, we'll do this one. So like right here, if you look at this, this is the block diagram to a power factor calculator. So this is all the information you use to set it up, to build the back end of it. So when you buy the eControls device, you don't see the back end, you see the front end. Now this is, this is kind of hacked together, this power factor block. So this is all the back end. This is the front end, and it all gets designed on a template. X. Don't save all. Let's do that. It all gets designed on what you call a blank virtual instruments. You start with these two programs here. So let's say, we'll start here. Let's say, let's go to Express. We'll start up here. Let's take a structure. We want to put a while loop. Okay, let's take a Express. We'll take an input, a DAC assistant. Why didn't that go there? Input, DAC assistant. Now your DAC, the data acquisition device, which the older eScope limited scope is a data acquisition device. It's a device that acquires signals. The ECOM controller for PSI is a data acquisition device. And basically, you can say, okay, I want to acquire a signal, whatever the device is, whether it's a CAN bus, whether it's an oscilloscope, a multimeter. There's certain different companies, devices that just have different analog inputs and digital inputs and analog outputs. You can actually control outputs on this. So you build it. There's no device found here, but if I had a device hooked up, I could build the DAC, and then I could create all controls and indicators, and then it would show up on my front panel if I actually had a palette. And then we can on the front end over here, we can add, let's say, a push button. Just, let's say, maybe we can add, and you can get different, you know, icon packs like the one that used over here. Let's see, so vertical switch, toggers, so let's say data containers. Trying to find something that looks, so I can take a graph, say take a waveform chart, and now I got a waveform chart here. Let's see, like right here, they're just showing, this is where you look at your oxygen sensor. So, you know, they got buttons and you can name your buttons. So, you know, an OK button, and then you can name it, let's say, let's name it clear. You know, so you can name your button. You know, so you can build your own program just like PSI and IMCO built their own program, all used on National Instruments. And if you look at, let's see if we find about. If you look at about here, does it say anything about National? Yeah, right here, National Instruments, which that's what my scope is built on. So kind of neat. That was just a little extra. So hopefully one day, I'm starting to work on a program to actually kind of extract all the junk data that we don't need out of this and kind of make a simpler front end that we can use on all the units. So you don't have to get the IMCO and PSI software, so you can just have one program that'll connect to both. That'll kind of be neat. So other than that, I kind of enjoyed talking to two people. That's about it. I'll try to do this once a week. Any questions, put them in the comments. Hopefully I get more people watching. I guess I'll let some people know. I got to put a little reminder out. If there's anything you want me to cover, if there's any other younger technicians or whatever, or have any, my hope is to, like, if any other technicians have a problem during the week, I could come on at night and kind of look into whatever their problems were. So, you know, go over a schematic or whatever, or say they're going to work on something tomorrow, you know, one of my coworkers or whatever, maybe kind of go over the schematic and kind of try to do like a virtual instruction lesson on whatever they were going to do. You know, if it was a repair or some troubleshooting they were going to do, maybe give them a little list of what to look for, and, you know, gather the schematics and all that, and kind of go over the theory of operation. I don't know. I like streaming. It kind of gets me more. I don't know how to say, more. Not involved, I guess. Just going over all the data and stuff actually makes me think of stuff. It really. I'm at a loss of words for what it does. It kind of. It helps me out with the diagnostic process. It kind of verbalizing what I'm thinking, and I kind of think of new things. So it stimulates the diagnostic process, I guess, is what I'm trying to say. So hopefully someone finds it useful. I saw a few people jump in and out. I am going to end the stream because I am losing my voice from talking so much. So that is it. Have a wonderful night. Cheers.